Okay, here are the solutions to the 2.8 activity on related rates. Let's see, I think I completed three of them here that I'll walk through, and then one of them that we can do out. So number one says a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius of the outer ripple is increasing at 1 foot per second. When the radius is 4 feet, at what rate is the total area of disturbed water changing? Okay, so here's how I would start thinking about this. The last statement says total area of disturbed water changing. Okay, well, so I know I need to be able to represent the area of that circle. And so the area of a circle is pi times the radius squared. Now I would go back a step in this, and it says, how is it changing when the radius is 4 feet? Well, that's when the radius is equal to 4 feet. And the radius, and finally, the last piece of information is the radius of the outer ripple is increasing at 1 foot per second. So the radius, that's a rate of change of the radius with respect to time. So that thing underlined in orange is dr dt as 1 foot per second. And what are we asked to find? The rate that the total area, the rate of the total area is the rate of the area with respect to time. So that would be dA dt is the thing that we're left to find. Okay, when we lay that all out from the given information, we can take derivatives with respect to time starting here. And we have that dA dt, so the derivative of a with respect to time, is 2 pi times the radius. The 2 comes down, we go to 1 less power. But we have to apply the chain rule, times dr dt, because r is the inside function. And now we can just fill in our given information that we've organized neatly. The radius is 4, dr dt is 1. We can solve for dA dt, and we should get 8 pi. And area is measured in feet, so that would be square feet per second. Okay, the second should look similar to the one from the introduction. Air is being pumped into a spherical balloon at 4.5 cubic inches per minute. Find the rate of change of the radius when the radius is 2 inches. Okay, so let's see. We have a few things. The rate of change of the radius, that's the thing we want to find right here. That is dr dt. We want to find it when it's 2 inches, so that's when r is equal to 2. And air is being pumped into a balloon at 4.5 cubic inches per minute. Well, cubic inches is a measure of volume. So cubic inches per minute is a change in volume with respect to time. And so that is dV dt. So now I need to relate the volume and the radius of this spherical balloon. And the volume of a sphere is 4/3 pi r cubed. So right here is the volume of a sphere. Okay, and so now starting from this volume, I can take derivatives so that I can relate to dV dt and dr dt. And on the left-hand side, I get dV dt. On the right-hand side, the 3 comes down. 4/3 times 3 is 4. I get pi r squared times the derivative of the inside function, which is r, and the derivative of r with respect to time is dr dt. Now I can take all that given information. I have 9/2 for the rate of change of volume, 2 for the radius, and I can solve for dr dt, and I get 9/32 pi. And in this case, let's see, we're measuring in inches, so inches per minute. All right, number 3. An airplane is flying at an altitude of 6 miles and will pass directly over a radar tracking station. If the distance from the plane to the radar is changing at 400 miles per hour, when the distance is 10 miles, what is the plane's ground speed? Okay, here all I've done is drawn the picture. There's a plane, it's 6 miles high. There's the radar. I've labeled the distance from the plane to the radar along the ground as x, and then the actual distance from the plane to the radar as z. Okay, so now we got to get a hold of some of this information. So if the distance from the plane to the radar is changing at 400 miles per hour, that is the distance from the plane to the radar along the hypotenuse of this triangle. So that's the distance measured by z. So that is dz dt. is 400 miles per hour. When that distance is 10 miles. Okay, so this is all happening when z is equal to 10 miles. What is the plane's ground speed? So the ground speed of the plane would be how fast the plane is moving in this direction is the ground speed, and that would be how x is changing. So we want to find dx dt. Okay, so we need to relate x and z somehow so that we can use what dz dt is to help us find dx dt. And the way we can do that is we can relate them in this right triangle here. This is a right triangle. The sum of the squares of the legs is the same as the square of the hypotenuse. It's the Pythagorean theorem. It tells us that x squared plus 6 squared is equal to z squared in this picture, or that x squared plus 36 is equal to z squared. Now we're going to take derivatives here. Derivative of x squared with respect to time. Again, we're going to need the chain rule. So the 2 comes down, we go to 1 less power. We multiply by the derivative of what's inside. And now the derivative of 36 with respect to time is just a constant, so its derivative is 0. And similarly, the derivative of z squared with respect to time is 2z times the derivative of z with respect to time. Okay, we should have all the information we need, except we don't know what x is, right? What do we have? We want to find dx dt. We have 2x times dx dt is equal to 2z, which we decided was 10, times dz dt, which we decided was 400. So if we knew what x was, we could go ahead and find dx dt. And the key thing is we want to find x when z is equal to 10. So up here, let's change the color. Up here, we need to find x when z is equal to 10. So x squared plus 6 squared is equal to 10 squared. And you should be able to do that algebra. Let's see. 100 minus 36 is 64. The square root of 64 is 8. So when z is 10, x is equal to 8. So in here, we need to put 8. And so we get 2 times 8 times dx dt is equal to 2 times 10 times 400. Oops, we can do that division. The 2's are going to go away. 400 divided by 8 is 50. 50 times 10 is 500. So we should be able to see that dx dt is 500 miles per hour. And that's the ground speed. So again, the key is getting down all of the information that's given, deciding how to relate the variables. In this case, we need the Pythagorean theorem, taking derivatives, and then solving for the missing piece of information. Okay, one more example to go through here. A rocket is rising with position function given by s of t is 50t squared and is being filmed by a camera 2,000 feet away from the launch. Find the rate of change of the angle of elevation of the camera at 10 seconds after liftoff. Okay, so I've drawn the picture. The rocket's going up given with a function given by 50t squared. The launch was 2,000 feet from the camera. And it says I want to find the rate of change of the angle of elevation of the camera. So right here, theta is the angle of elevation of the camera. So I want to find d theta dt. And it says do that 10 seconds after liftoff. So when time is 10. Okay, so let's look at this picture. What do we have? The only way we can relate, we can get an expression for theta in terms of t pretty easily by using tangent. We know that tangent is the opposite side over the adjacent side of a right triangle. Here is our right triangle. And so the tangent of theta is 50t squared divided by 200, which looks like we could do some simplification there. That's 5 over 200t squared. And from here to here, we can take derivatives with respect to t. So on the left-hand side, the derivative of tangent is secant squared theta times the derivative of that inside function theta, which is d theta dt. But here now we have a function of t on the right-hand side, so we can just take its derivative. So we get 100t over 2000 when the 2 comes down and we go to 1 less power, which is t divided by 20. Okay, so now we need to analyze this situation at t equals 10, right? So what we're interested in what's happening at t equals 10. Well, I can easily plug 10 into the numerator of the right-hand side, but I have to do a little bit of work on the left-hand side to get my hands on secant squared of theta, because the thing that I want to find is this. So I need to get my hands on secant squared. So let's see. At t equals 10, our triangle looks like this: 2,000 feet, 5,000 feet, and theta. So the tangent of theta is 5,000 over 2,000, or 5 halves. Now we can remember one of our trig identities: tangent squared plus 1 is secant squared. I have an expression for tangent, it's 5 halves. So 5 halves squared plus 1 is secant squared. 5 halves squared plus 1 is just 29 over 4 and is equal to secant squared. But that's exactly what I have over here, is an expression that includes a secant squared. So I'll replace that secant squared with 29/4, and now I have all the information I need to solve for d theta dt, and it's 2/29, and that measurement would be in radians per second.